Hello, I welcome you all to this another interesting screencast. The problem reads, the pulley has a radius of 3 inches and fits loosely on the 0.5 inches diameter shaft. If the loadings acting on the belt cause the pulley to rotate with constant angular velocity, determine the frictional forces between the shaft and the pulley. Determine the frictional force between the shaft and the pulley and compute the coefficient of kinetic friction. The pulley weighs 18 pounds. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. Right, so we have a pulley of radius 3 inches and it loosely fits on a 0.5 inches diameter shaft. We have been given the weight of the pulley, which is 18 pounds, and we are being asked to determine the coefficient of kinetic friction and the frictional force between the shaft and the pulley. All right, so let's redraw this particular system so that I expand the shaft a little bit. So let me make the shaft maybe this big. Sorry. Okay. So imagine this is the space within the pulley. This is the outer diameter for the pulley. I'm exaggerating the diameters. Now let me draw the pulley. But before I draw the pulley, I want to explain a few principles. We have been given, on one side, we have the weight. On one side, we have the weight or the belt over the pulley is 5 pounds. Then on the other side, let's say it was T. Okay. So there is a point where the pulley is in contact with the shaft, right? So imagine T was equal to 5 pounds. Where do you think the contact would be between the shaft and the pulley? So if we are to draw this, it would be something like this. Okay. I'm just exaggerating, right? It would be exactly here, vertical. It would coincide with the point where the gravity passes. The gravity, I mean the weight of, so if this was the weight of the pulley, which is 18, it would coincide, right? This would be the point of contact. Point of contact between the shaft. This is the shaft in green, and the pulley. So imagine we increase this T on this belt, we increase it, let's say, to 5.5. What do you think would happen? The pulley, imagine the pulley is experiencing impending motion. Which direction would that be? Of course, you know to say, if we increase the tension to that end, I mean to 5.5, then you have impending motion in this direction. Okay, then what happens to the contact? The contact shifts. It shifts, right? It would shift from that point to right? Let's put blue. It will shift to the right to shift to the right. Let me use blue. It would be somewhere there. And if we were to draw this, it would be something like this, right? Something like that. Not too good enough. Okay. So it would shift to the right. Okay. So t was equal to, what if t was equal to uh, 4 pounds? What would happen to the point of contact? The point of contact would shift to the left, right? In blue there like this. So we see the contact shifting, and it is at this particular point of contact where we are experiencing the normal force as well as the frictional force, right? This is what we want to reduce because it wears out both the surfaces of the shaft as well as the pulley. Okay, so we see the point of contact shifting and changing. All right, and that is at the same point where normal force and the friction force is taking place, or that's where we are having those reactions. All right, so having said that, let's now draw our free body diagram. The same one, we just want to add more details. Okay, all right. So when we look at our point of contact, where is it? It is to the right. It is somewhere where there. So it means impending motion is in this direction, right? And moreover, it just makes sense because when you look at the force on one side, it is higher than the other one. Therefore, the pulley would tend to move in a clockwise direction, right? Okay, so let's put that point of contact somewhere there like so, and then draw the shaft. So the shaft will be something like this. We draw, I may not be very perfect, something like this. All right, so let's imagine it is something like that, and this is, let's put the center of the that is the center of the pulley. We put the center of the pulley and we put the right tension there, which is 5.5 pounds. What else? We've been told the weight for the pulley, and the weight is 18 pounds. Okay, what else? So now we have the diameters given. Diameter for the pulley, this diameter is, radius is 3 inches, and the radius for the shaft, let me indicate it, the other side is that's half of 0.5, so this is 0.25 inches. Okay, the impending motion in this particular case here, as we can see, the impending motion, the point of contact is to the right. Moreover, the force on one belt is higher than the other one, as you can see here. Therefore, we'll have impending motion in this direction like that, right? Okay, so therefore even here the impending motion is going to be in this direction. All right. So we have this point of contact. This is where the friction forces, or the friction force and the normal force, will be acting. The resultant of the two, which is R, the resultant of the friction force and the normal force, R, is always in this direction, which is the vertical direction, like so. Okay. Since impending motion is in the clockwise direction, you expect friction to be in that direction, like that. And then you have the normal force like that. Okay. Let me use another color, maybe blue. So friction will be in that direction, like that. And then you have the normal force in that direction, like that. Okay. And then this angle here between the normal force and R, you said this is R. Between the normal force and R, this angle here is called the angle of kinetic friction. This is the friction due to the two contacting surfaces in motion. Okay, which is phi subscript k. We also have another distance from the center to the point where we have the resultant force R, this that we are calling R subscript F. Okay, this R subscript F is called the friction circle. Okay, this is the friction circle, which is this distance here in red that I'm just showing right now. Okay, and the R itself is always in contact with this particular circle. Okay, it's always tangential to this circle. All right, so this is the distance here, which is RF. We'll need this. It will help us be able to compute our equations of equilibrium. All right, and when you look at this RF, when you just do some trick there, you realize that your RF, let me write this outside so that it doesn't confuse you or anyone. This one here, that angle we said is phi k. Okay, so that I just rub this, I empty this, becomes clean. And then this is our RF, this distance here. Okay, and RF, if you are to do the trick there, your RF is going to be equal to the radius of the shaft, which is R shaft. Okay, or just say R radius of the shaft, and then times sine phi k, right? That's all. Radius of the shaft sine phi k, that is the friction circle. Okay, so let's call this point of contact. Let's call this point of contact as point A. Okay, point of contact. So we are saying A is the point of contact. Right. So we are going to apply the equations of equilibrium now. Let's apply them. We are going to take moments about point A. We'll take moments about point A so that we find the friction angle. And we know that the friction mean the coefficient of kinetic friction. We know that tan phi k is equal to mu k, which is the friction coefficient of friction, coefficient of kinetic friction. But if mu k is so small, this is in the point where the surface between the shaft and the pulley are lubricated, then you can have a condition where sine phi k is approximately equal to tan phi k, which is approximately equal to mu k. Alright, this condition happens when the coefficient of kinetic friction is so small. Then you can have that approximation, but we are going to use the first one, which is tan phi k equal to mu k. So let's take moments about point A. So we'll say summation of moments about point A equal to 0, anti-clockwise being our reference. So what do we have? We have a 5 times the lever arm 3 plus 0.25 sine mu k. Remember this term? This term is the friction second, the distance itself, or the radius of the friction second. Okay, and then minus 5.53 minus 0.25 sine mu k. Again, this is not the only way to solve this. This is just one of the ways you can solve them. You can solve this problem differently. You can take summation of forces in the y, you find r, and later on use r to work out the problem. You know r itself, and what else? Anyways, this is one of the ways to do it. Okay, and not the only way. Then plus what else do we have? We have 18 giving us a positive moment, 18 by 0.25 sine mu k equal to 0. Okay, are we good? Making sine phi k subject to the formula, we're going to have a 1.5 divided by 14.25. Making phi k subject to the formula, we want to find what this angle is. If we did so, we find that this will give us a 12.15 degrees. And therefore, we said tan phi k is going to be equal to mu k. And therefore, replacing mu k there, replacing phi k there, we'll find that our mu k is going to be equal to tan 12.15. This gives us a 0. 0.2153. Okay, so we are also being asked to determine the friction force. So let's find R very quickly. Let me use this space here. So summation of forces in the y direction equal to 0. What do we have? We have minus 5, minus 5.5, minus 18, then plus r equal to 0. Therefore, our r is going to be equal to minus 5 minus 5.5 minus 18. This is a 28.5. From trigonometry, we have r, we have n, and we have f, and we have the angle in between our phi k. F, therefore, is going to be equal to r sine phi k, which is equal to 28.5 sine 12.15. F is going to be equal to, therefore, 28 times sine 12.15. This gives us a 5.99, which is a 6. Alright, so a summary of the solution. We have mu k, which is the coefficient of kinetic friction equal to 0.2153, and we have the friction force, which is equal to 6 pounds. So this is about it. This is the final solution. We found the coefficient of kinetic friction at the point where the shaft is in contact with the pulley, as the pulley rotates with a constant angular velocity. And we've also found the friction force between the shaft and the pulley. And I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and sharing my channel. Bye bye, and see you in my next screencast.